Hi everyone. In this video I will be providing another demonstration of an application of multivariate multi-level modeling. And the example that I'm going to be working from is one that is provided by Pittock and Stevens in their 2016 text, Applied Multivariate Statistics for the Social Sciences. And in particular, this is coming from chapter 14. So as I go through the demonstration, I'm going to be walking through a lot of the procedures that they talk about. They actually, in terms of providing instruction with respect to SPSS, they actually spend most of their instructional efforts on showing you syntax for how to generate the results. But in this video, I'm going to be walking you through the menu systems, or rather the point and click interface. Now, before I get started, I do want to mention a couple of things. First off, underneath the video description, you'll find links to the data sets that I'll be working from in this presentation. So you can download a copy of those SPSS data files to follow along. You'll also find a link to a PowerPoint that I've put together as a supplement to this presentation, so you can access that by following the link to learn more. One other thing that I do want to mention too is I'm not going to be going over every aspect of multivariate multi-level modeling in this presentation. There's just way too much that I could theoretically talk about, and things can get bogged down really quickly. So I'm going to be focusing my attention on just the basics of how to structure the data and to carry out the analysis and some basic interpretation in this video. But I do strongly encourage you to read up more on this topic, and in particular on the examples that I provide, maybe by going to that Pittock and Stevens text, and in particular chapter 14. And one other thing that I will mention too is that the last examples that I provide in this presentation, I'm actually kind of diverging from that presentation in the text. In the text they actually kind of talk a little bit about how to recode and things like that. And again, I just didn't want to bog things down in this video. So let's go ahead and get started just by considering the data set. And as I kind of go through and was thinking about putting this together, I wanted to kind of give you a little bit more of a real life kind of feel for how you might deal with data in this kind of multi-level sense. So what you see on your screen is data as it's provided in wide format. And briefly, the example data that we're working with, this is simulated data for their presentation. And basically each row in the data set represents a student associated with a given school. So you can see that we have the student variable right here. This is the student identifier in the data set. And so each row, there's 800 students in the data set, so there's 800 rows. And so because there's one row per student, the data set we can say is basically in what's called wide format. And so to carry out our analyses, we're going to actually need to restructure the data into a long or vertical format. So, but as we look at the data set, again, we have student identifiers and we have school identifiers. So there are 800 students, and those students are nested within one of 40 schools. Now, this variable right here, treat, this is a treatment variable, and basically the way the scenario is laid out is that we're going to be testing the effect of a couple of interventions on students, kind of knowledge and intentions with respect to eating healthy. So the treatment variable is actually coded 0.5 to represent kind of the experimental treatment, if you will. It's kind of like a computer games based treatment or intervention, or kind of a curricula, if you will. A value of negative 0.5 reflects kind of the traditional instruction. And so in the scenario, basically schools were randomly assigned to either kind of the treatment or the control condition, either the computer game based approach or the traditional approach. So the data was collected kind of using a cluster randomized sampling approach. So as you can see, basically all of the students within a given school, like you can see all of these students right here who are in school 1, all of those are going to have the same code with respect to the treatment variable, and then all of those in in school 2 will also have the same code as well. So that's kind of at the level, that's where the treatment variable is kind of being enacted. So again, the schools are randomly assigned to the different treatment conditions, and then the students, by virtue of being members of those schools, are receiving those differential treatments. You'll also see in the data set that we have student gender. It's actually coded -0.5 for students identified as male and 0.5 for students identifying as female. And then our outcome variables are intention and knowledge right here. So intention to eat healthy, and then we have knowledge about eating healthy. You also see that in the data set we do have these other two variables, but we're not going to be concerning ourselves with them. So as I said, this data set is in wide format, and we're going to need to start off by restructuring it into vertical or long format, so that each student's responses are going to be contained across 2 rows instead of 1. And the reason why it's going to be 2 rows is because we're going to be capturing the responses to intention and knowledge in a new variable that spans 2 rows. So let's go ahead and restructure our data by going to Data and Transpose. Oh, excuse me, not Transpose. I don't know why I was going there. We'll go down to Restructure, and we will stick with what do you want to do. We're going to restructure our selected variables into cases. So I'll click on Next here. Then how many variable groups do you want to restructure? We're going to stick with 1 because we're just going to be creating 1 response variable that contains the information from both the original intention and knowledge variables. So we'll click Next, and then under here we are going to move our intention and knowledge variables over to the target variable box, and we're going to have to give this new variable a name. So we'll call it, just kind of keeping in line with their presentation, we'll call it response. And then, excuse me, I hit enter inadvertently, but basically you can see that it shows up down here as response. So now where it says fixed variables, all the values that we have on the other variables, we actually are wanting to maintain those values across rows because those are essentially constants that we want to maintain. So in order to do that, I'll go ahead and select all of these variables right here up to, but not including intention and knowledge. I'll select them and move them over to the variables box. And then, let's say for instance we wanted to maintain these other variables, we could certainly do that. So I'll just go ahead and select these as well and move them over. And at this point we'll press Next, and then it asks how many index variables do you want to create. So when we restructure our data from wide to long format, again we're going to be creating a new variable in the data set that contains the intention and knowledge responses. So it's going to be a single variable with responses to those measures. So we'll have one row that has the intention value, another row for a given student will have the knowledge value. And so we need to be able to index what those rows are actually representing. So we're going to request a single index variable in order to help us to identify which variable is reflected in a given row. So we'll click on Next right here, and we can go ahead and actually click Finish. And so now when we look at our data set right here, we have the data is now in long format. You can see that we actually have a new identifier variable here. It's actually the same as the original right here. And you can see that student 1 right here is in school 1, and you can see that we have this index variable right here coded 1 and 2. The 1 is reflecting the intention variable, 2 is indexing the knowledge variables, and the responses for student 1 for each of those is contained in these first 2 rows. And you can see for the second student that's also in school 1, their intention response and then their knowledge response associated with the index values of 1 and 2. So once you've got the data restructured, the next thing that we need to do is be sure that we save our data set. We don't want to overwrite our original data file. So right now we have the original data file up here at the top, and so we want to actually save this under a new file name. So I'm going to click on Save As, And in this case, I'm going to call this, I'm just going to overwrite an old file, which I'll call nutrition2 rev_1 right there, .save. So we'll click on save right here, and I'm just going to go ahead and overwrite, so that now I still have my original data set if I need to go back for whatever reason. So at this point, we can begin to carry out our analyses. So in that Piddock and Stevens chapter, they actually start out with the first demonstration of how you could theoretically use multivariate multi-level modeling in order to carry out what amounts to be a multivariate analysis of variance, or a MANOVA, if you will. So what I'm going to do is start off right there, and when we're doing this, we're going to treat, for the purpose of this first demonstration, we're going to treat students as not being nested or clustered within schools. We're just going to treat it all as kind of at the student level, and so we're going to ignore any clustering that takes place. And that's really what happens in the context of, say, a MANOVA. We're not going to be, if we carry out a MANOVA and we're testing something like the effect of a treatment on dependent variables, we're not acknowledging any type of clustering that may be taking place. And if there is clustering, by the way, then that can produce inaccurate inferences in the form of type 1 error when it comes to testing those treatment effects. So we're starting out by kind of simulating or carrying out what amounts to be a MANOVA by way of multi-level modeling, just to show you how you could do that if you wanted to. And there are reasons that are discussed in that chapter that I'm not going to go into right here. And then from that, we're going to move into other analyses at this level, and then also we'll subsequently incorporate school as our clustering variable. So to carry out our first analysis, what we're going to do is go to Analyze, go down to Mixed Models, and then click on Linear. And then where it says Subjects, I'm going to move this ID variable over, the student level identifier. And then where it says Repeated, I'm going to move the index variable over here as well. And then where it says Repeated covariance type, I'm going to kind of scroll down a little bit and select Unstructured. So what's going to happen in this first analysis is essentially going to be generating a null model where there's no predictors in it. And the reason why this matters is because when we test the multivariate effect of treatment on our repeated measures, if you will, or outcome variables, we need a baseline model in order to compare against a model that incorporates the treatment effect. And I'm going to be showing you how to do that test later on in the form of a likelihood ratio chi-square test. So that's kind of where we're starting out at this point. So I'm going to now click on Continue, and then select my response variable. So I'm going to move this to the dependent variable box. I'm going to move the index variable over to this factors box right here. And then where it says fixed, I'm going to click on that. And I'm going to deselect where it says include intercept at the bottom. I'm going to deselect that. Now, ordinarily when you're running multi-level models, or typically when you're running multi-level models, this will be clicked, but in this case we are going to deselect that, and we're going to move our index variable over to this model box right here. So then we'll click on Continue, and we're not going to do anything under the random box at this point, because as I said, we're only going to be treating our data as if it was occurring at at the student level only, and there's no clustering that's taking place in our data. So we're not going to be using this random box right here, where we would ordinarily click on it and click on some options in a more traditional multi-level analysis. So now we'll click on Estimation right here, and you'll see that we've got two methods that are presented. We're going to stick with the method that they give in the textbook, which is maximum likelihood estimation, and we're also going to click on residual methods. So just kind of FYI, if you happen to go back and you start reading the chapter, you'll see that there's nowhere there's any kind of mention of these kind of different options in terms of these degrees of freedom methods and so forth. And the reason why is because they were actually referring to an older version of SPSS. This was back in 2016, right now this is 2022 as I'm putting this together, and I'm working with SPSS version 28. So a few of the bells and whistles have been added. And so just kind of keep in mind that in order to reproduce their results, you'll need to select maximum likelihood right here and then residual method right here. So at this point, we'll click on continue, and then where it says statistics, I'm going to select parameter estimates for fixed effects, test for covariance parameters, and covariances of random effects right there, and then we'll click on continue. And so now we're ready to run our basic analysis. So I will click on OK and generate our output. So first off, just keep in mind that if you look at the model dimension table, you're going to see kind of a breakdown of the different effects associated with this model. So we have fixed effects, and we have two parameters that are estimated. And so the fixed effects in this model are going to be estimated grand means for our intention and knowledge variables. So that's why you have two parameters that are estimated here. Then we have the repeated effects, and you'll notice that we have a 3 right here. And what is going on is that we are estimating the variances of the intention and knowledge variables as well as the covariance between them. So because of that, now we have a total of 5 parameters that are being estimated for the model. Now when we scroll down a little bit further, you'll see that we have this table containing information criteria, and this is general information for evaluating the fit of a model, but typically these are not terribly helpful in and of themselves. They're usually most helpful when you are comparing models. So it's really, you can't really do much in the way of well, really anything with them, so long as you're just kind of looking at the fit of a single model. But if you're looking at model comparisons, that's where these are handy. So I'm going to draw your attention right here to this first index, which is the -2 log likelihood. This is referred to as the model deviance. And the model deviance, as I said before, this is an indicator of model fit. And so a perfect model, or perfect fitting model, is one where the deviance would be 0. And that's really not going to happen in any case unless you have, say, a saturated model. But basically, as you move towards higher numbers in the positive direction from 0, in that case, that's reflecting a worsening in fit. So the larger the number, the worse fit. The smaller the number as it approximates or gets closer to 0, the better fit of your model. And this is going to be relevant later on because we're going to be testing the fit of this null model against a model that contains that treatment predictor. And so all things being equal, by adding in the treatment variable, logically that should result in a reduction in the model deviance, and so the model that contains the treatment predictor should fit better. So that's kind of the way to be thinking about this. So just so you know too, we have these other descriptive indices right here that take into account things such as model complexity, and so these can also be useful for comparing models. So at any rate, we'll scroll on down and look at our tests of, or the estimates of fixed effects, and you can see right here the estimates in this column right here. These are the grand means for our intention and our knowledge variables. So as you're looking at this, you'll see that we have some t-tests associated with each of those estimates, and by and large, under most circumstances, it's really rare for someone to want to kind of report on those tests. And the reason why is because those tests are essentially testing the difference between the estimate over here and a null value of 0. And so typically that is not of substantive interest, so we're not going to talk about that right here. But later on, when we add in predictor variables, then in that case we will certainly want to look at the t-tests associated with those regression parameters. Then finally, as we look at the estimates of covariance parameters box right here, then you can see that we have in the estimate column, these are estimates. In the first case right here, this is the estimated variance for intention, and then we have the estimated variance for the knowledge variable, and then we have the covariance between the two variables right here. And so the reason why it says 1 1 2 1 2 2 is because you can think about these variances and covariances as being collected within a variance covariance matrix. So if you kind of think about it this way, if I kind of organize it in the form of a variance covariance matrix, then what we would have is the 1 1. If I treat the first 1 as essentially representing the intention variable, then we would have essentially that variance estimate appearing right here, the 119.951740. And then for the 2 2, that would be a variance associated with the knowledge variable. I'm just kind of check boxing or check marking the positions within a variance covariance matrix so you can kind of get a better sense of what's going on. So the 1 1 is for the intention variable right here, the variance there, and then the 2 2 is for the knowledge variable, and then the 2 1 is row 2 column 1. That right here is the covariance between those two variables. And then on the other side of our diagonal, that would also be repeated right there, but there's no need to reproduce that in this table right here. It would just be redundant. So at any rate, that's kind of how this is laid out. And so as you're looking at this, you can see also that we have walled z-tests that are used to test these variance components. And just so you know, the walled z is there's some debate about whether or not this is actually the better approach to testing these variance components. A number of authors suggest using a likelihood ratio test, but for this particular demonstration, I'm just going to keep it simple and just focus in on interpretation within the context of this talk and with this particular output. So as you can see right here, basically we have a test of the variance component, and we can see that we have statistical significance in terms of being different from 0. The variance components right here, we have a test and it's different from 0, and then we have the covariance right here, which is basically we can see that we have a significant covariance between the intention and knowledge variables. So that's how to kind of make sense out of those tests. Like I said, there are other suggestions for how to perform tests of these different variance components, but I'm just kind of keeping this fairly straightforward for this particular demonstration. So now let's run a model, and we're going to incorporate our treatment factor, if you will. So to carry out this analysis, we'll go back to Analyze, we'll go to Mixed Models, and then go down to Linear and Continue. And now we'll add in the treatment variable. So one thing to draw your attention to also is that the treatment variable in the data set, it is essentially effect coded. So with effect coding, basically what that means is that we have the values for our two levels, in this case coded -0.5 and 0.5, and that does have some implications. How you code your treatment factor or whatever is going to have some implications for how you make sense out of the estimates in the next model. But at any rate, I'm just kind of drawing your attention to that as we move forward. So I'm going to move the treatment variable over to the covariate box and click on Fixed. And so at this point, we're going to be adding in an interaction effect. And so to do that, we will highlight both of these variables right here, and you can see where it says factorial. We can just click on Add, and it adds that interaction effect. Now we also want to get rid of this variable right here, the treatment variable by itself, and so that's just kind of the way this is carried out, and this is also going to help to really facilitate our interpretation. So at this point, we'll click on Continue, and we have pretty much done everything that we need to do at this point. So again, we're essentially treating our data as if it's not clustered within a higher level unit such as schools. So we're just kind of treating it all as at the same level. So now what we'll do is we'll click on OK, and leaving all of the other options selected. And so as we're looking now, you can see that with our model dimension table, you can see that we have, once again, we have estimates with respect to our grand means for our two variables. Then we also have regression parameters that are generated that capture the differences between the two groups with respect to each of our repeated measures, or dependent measures, if you will. So in other words, we'll have a regression coefficient reflecting the difference in means between the two groups with respect to the intention variable and also the knowledge variable. And then we still have our repeated effects variance covariance matrices reflected here. So when we add all those parameters up, we come up with 7. And you can also see that we have this -2 log likelihood. There's our deviance value for the current model. And so when it comes to carrying out a test of the omnibus effect of treatment, then what we would be doing is we would be comparing this deviance value for the current model against our previous deviance value associated with the null model. And the way that we do that is through a likelihood ratio chi-square test. And if we find significance in terms of that test, that would be an indication that the current model fits significantly better than the null model. Well, if the current model incorporates only or incorporates a treatment effect, whereas the other model does not incorporate any predictors, then it stands to reason that that would be a test of the omnibus effect of treatment. So I'll show you how to do that shortly, but I'm just going to go ahead and proceed through looking at the remainder of the output. And so as you're looking at this, you can see with our estimates of fixed effects, once again we have the grand means for our intention and knowledge variables, and then we have the regression slopes that are used to test the differences between our two groups. Once again, our treatment group, the traditional instructional approach, is coded -0.5. The approach that's kind of the computer games based approach is coded 0.5. So this difference that we see right here is a difference in means between the two groups with respect to intention. And so you can see that there is a significant difference, and it appears that individuals in the computer game based approach is scoring higher on intention than those in the traditional approach. Then with respect to the knowledge variable, you can see once again there's a significant difference kind of favoring the computer games based approach over the traditional approach. As we look at the estimates of covariance parameters, we once again have our variance and covariance estimates that are given right here, but these are after we've taken into account the treatment effects that we've just talked about above. So now let's go ahead and take a look at carrying out that likelihood ratio test that I was talking about. So the way that we do this, and basically it involves taking the deviance. Really, the larger deviance is going to be associated with the null model. The smaller deviance is going to be associated with our model that contains the predictor. So we would take the larger and subtract the smaller, and that's going to get you a difference in deviances, which is distributed approximately as chi-square. And so then in terms of the degrees of freedom, that's going to be calculated as a difference in the number of parameters between the two models. So if we look here, you can see once again the number of parameters in the current model with treatment is 7. The number of parameters that are estimated in the model without the treatment variable incorporated is 5. So you can see over here there's our 5 that's listed. So in the interest of kind of expediting things a bit, what I've done is created an Excel spreadsheet with the computations, and so I'll walk you through the basic computations. But you can obviously carry out these analyses on your own. A lot of times you can just do this by hand if you wanted to. But again, here's the Excel spreadsheet, and I'll include a link to this underneath the video description for those of you who are interested. So you'll see up here that I've set up, basically this is the deviance or the -2 log likelihood for the null model. And for that model, we had 5 parameters that were estimated. For model 2, with the treatment variable added, here's our model deviance. And as you can see, and as one would expect, as we move from a model with no predictors to one that incorporates at least one predictor, we would expect that deviance value to decrease. And so as I noted too, with respect to deviance, if we have two models, the better fitting model is actually the one with the smaller deviance value, because that means that that model has less misspecification or lack of fit than the other model. So that's the way to kind of think about it. So over here, the chi-square value is just computed as the difference between those two values. So I just took the larger deviance value, subtracted the smaller, and that's what gets me the chi-square value of 182.558. The degrees of freedom is just computed by taking the difference in the number of parameters. So I just take the larger, subtract the smaller, and obviously we have 2 degrees of freedom here. So, one way of carrying out the test is just to you can basically look up the chi-square test value in the back of any stat textbook, maybe assuming a p-value or an alpha level at 0.05, and you can kind of compare the chi-square value you have here against the chi-square value that's tabled, assuming 2 degrees of freedom. Or in the case right here, what I did was I just generated a p-value for this particular test. So the way that I did this, by the way, in case you're interested, I just typed in, found a cell, and I just typed in equals, then CHISQ dot DIST dot or period RT, and then I selected for the first term right here the chi-square value, comma, and then the degrees of freedom, and you'll see it kind of prints it out in scientific notation, but you can change this if you want just by going to format cells, and you can kind of change this to number right here, and there's your p-value for that particular test. So as you can see, by virtue of our chi-square test, or our likelihood ratio chi-square test, what this is telling us is that there is a significant omnibus effect of treatment on the set of our dependent variables, our repeated measure, if you will. That's, again, I'm using the term repeated measure in reference to the response variable, because that's essentially how this is being modeled for this particular analysis. Okay, so I'm going to go ahead and remove that, and now what we'll do is we'll carry out another test. Now, one of the things that's kind of nice about the multivariate, multi-level approach is that, in addition to kind of testing and kind of generating our results like we would in the context of a MANOVA, we can actually test for differences in the effect of our treatment variable across our dependent variables. So in other words, maybe the effect of treatment on intention is different from the effect it has on knowledge, or perhaps maybe treatment has a very similar effect on each of those measures. And so what we can do is we can test whether we have an invariant effect of treatment on the intention and knowledge variables, or whether the effect is non-invariant. So what I'm going to show you here is how to perform essentially an invariance test of the effect of treatment on the two outcomes. So the way that we can accomplish this is by going back in, as we had done before, and where it says fixed, in this case we're going to move this little interaction variable out, and we're just going to add in the treat variable right here. And so what that's going to do is it's going to generate, instead of 2 separate regression coefficients for the effect of treatment on intention and then one on knowledge, in this case it's going to generate just a single regression parameter, and the assumption would be that treatment would be having the same effect across those two outcome variables, if you will. So that's why there's only going to be a single regression parameter that's generated. So we'll click on continue right here and then on OK. And so now as we look at our output, you'll see first off that in terms of the effect of treatment, there's only one parameter that's being provided right here. And so when you add all those parameters up, that's what's giving us 6 parameters total. So what we'll want to do is to test whether the fit of our previous model differs significantly from the current model. So because we are constraining the effect of treatment to be equal across both of our response variables, then the effect should be to have a model that fits worse than what we had before. So the expectation would be that the model deviance would actually be higher than what we had previously. And so we can test whether there's a significant difference in fit from our previous model where we were treating the effective treatment on the response outcomes as non-invariant versus this one where we would be treating the effect as invariant. So I'll go ahead and scroll down before we carry out that test just to kind of show you the remainder of the output. And so as you can see right here, we have our grand means for intention and knowledge right here. And then you can see we have this one regression parameter that's estimated at 8.6777. So that is the estimated effect of treatment on each of our response variables. So we're assuming that the effect of treatment is constant across those response variables. And you can see that effect is statistically significant. But that's basically all there is to it when it comes to generating those results. Now the next thing is if we want to test whether to actually perform kind of the proper test of whether there's whether the effect is invariant or non-invariant, then we're going to be using those deviance values and the degrees of freedom from the current model and the previous model. So what I did again was to create in my Excel spreadsheet a model 3 that contains the deviance value for the current model and our degrees of freedom right here. So the chi-square difference test is just basically computed by taking the deviance for this model and subtracting the deviance from of the previous models from it, and so that actually gets us a chi-square value in our spreadsheet here. Let me just kind of hit that of 0.015. So there's really not very much difference between those two models in terms of fit. And so with 1 degree of freedom right here, the p-value that would be computed is 0.9025. So clearly there's no significant difference in fit between our previous model that assumes non-invariance of the effect of treatment on our response outcomes and invariance, which is associated with this model 3 right here. Now do keep in mind that for this type of analysis to be carried out, you really need to have response variables or outcome variables that are similarly scaled. So just kind of keep that in mind as you are planning your research studies in the future. But nevertheless, you can see that there's no difference in fit. And so when it comes to evaluating, well, which model should I kind of gravitate towards, you can see then that there's not really a lot lost in terms of fit by just simply assuming an equivalence of the treatment effects. So from a parsimony standpoint, model 3 might be considered a more preferable model than model 2. Now another way to kind of evaluate that too is to look at the information criteria associated with both of those models. And so you can look at, in particular, I kind of tend to gravitate towards Akaiki's information criteria right here. And we use the same basic idea of one model, the AIC in this case would, for the better fitting model, would be lower than the worse fitting model. So the smaller AIC is associated with the better fitting model. And the AIC, you're not using it in a significance testing approach. Rather, the AIC is essentially kind of the deviance of the model, but it's adjusted for model complexity. So basically there's a penalty for more complex models, and so all things being equal, more parsimonious models are preferred. So that's kind of the logic behind the use of this index. So I can make the comparison between this model and the previous model, and you can see with the previous model it was 11,861.606. In the current model, you can see it's 1159.621. So in the current model, the AIC is actually where we have the assumption of invariance of the effect of treatment across the two response outcomes. You can see that this model would actually be considered the preferred model if we're using the AIC. So that's kind of the way you can think about it with respect to testing for invariance versus non-invariance of, in this case, the treatment effect. So now what we're going to do is move on to another example where in this case we are going to now acknowledge the clustering of student outcomes within schools. So we're going to now take into account the school effects, if you will. And that's going to be really important because, as we've talked earlier, all of these different, the analyses that we've carried out thus far have largely assumed that the students' responses are all independent of each other, and so that can lead to biases, in the standard errors for your associated with your test of your fixed effects, and that can inflate the type 1 error probability. So now what we want to do is to acknowledge clustering within schools. And so to carry out our analysis, we'll go to Analyze, Mixed Models, Linear again. And so where it says Subjects, now we're going to include the school identifier. And in fact, I'm just going to go ahead and move both of these over. So we're going to maintain the student identifier, but also the school identifier right here. And we can leave all of the remaining boxes clicked right here. We'll click on Continue. And we're going to also go back and under Fixed, even though we have pretty good reason to believe that the effect of treatment is actually perhaps, or should be modeled perhaps as invariant, what we're going to do is just kind of pretend, if you will, that the effects are non-invariant. We're just going to go back and kind of respecify the model with this interaction right here, leaving out this treat variable as I had said before. So now what we'll do is we'll click on Continue, and at this point, because we're incorporating this higher level clustering variable, if you will, now we're going to click on Random. And so when this box comes up, we're going to move the school identifier variable over to this combinations box right here, and then we'll move the index variable over as well. So we're essentially going to be allowing the intention and knowledge variables to randomly vary across schools. So where it says covariance type, we'll go ahead and scroll down and select unstructured. And basically that's all there is to it at this point. So now we'll click on Continue and generate our results. So as we're looking at our output, you're going to see in terms of the number of parameters, you can see that we have, again, our grand means that are being estimated for each of our variables, intention and knowledge. We also have tests of the differences between the treatment groups with respect to intention and knowledge. But keep in mind that previously we weren't really spending much time kind of acknowledging the fact that the treatment variable was reflecting the random assignment of schools to the treatment conditions, and now we can kind of think a little bit more clearly along those lines. So then you can see that where it says random effects and repeated effects, so we still have the variance and covariance for our intention and knowledge variables, kind of at the person level, if you will. But then we also can look at variance and covariance estimates across schools with respect to those variables. So when you sum all those effects up, they're going to sum to 10. So now we'll scroll down and look at our estimates of fixed effects and our estimates of covariance parameters. And as you're looking at the actual estimates in this column right here, you can see that they're basically the same as what we had before, but you're also going to notice something else. If you compare the results currently with those that we previously had, you're going to notice that the standard errors are larger. You'll also notice that the degrees of freedom, right here, you can see that they're smaller, and then the t-values are smaller. And this is all capturing or acknowledging the clustering effect that's taking place in our data. Again, we're acknowledging the fact that students within schools, within the same school, are going to tend to be more similar with respect to our response outcomes as opposed to students between schools. And so I know that in this demonstration I'm not going through and kind of walking you through the basics of testing the intra-class correlation and so forth, but that's the implication right here when we're looking at these differences in terms of the values of the standard errors, degrees of freedom, and the t-values. As we look at our estimates of covariance parameters table here, we have our variance estimate for intention, variance estimate for the knowledge variable, and then the covariance is given right here. So that's that's kind of occurring across individuals, within schools, and then across schools you can see that we have variance estimate for intention, knowledge, and then a covariance estimate as well. You'll notice then that in terms of the estimates within schools right here, you can see that all of those would be significant using the walled Z, whereas kind of between schools you can see that with respect to the variance estimate of intention, you'll see a p-value at 0.073, and actually it's discussed in Hawks's book and in Pittock and Stevens and others that technically speaking, when you're talking about using the walled Z for testing a variance component, such as the variance of intention and also variance of knowledge, you should be using a halved p-value, so basically half this value, in which case that would be considered statistically significant as well. With respect to the knowledge variable at the school level, the variance estimate, we have significance, and then but you can see that the covariance between the two is not statistically significant. Okay, so that is basically kind of a walkthrough of adding in the school clustering variable, if you will, for lack of a better way of putting it. Now let's run one additional model. This is actually not covered in the Pittock and Stevens chapter. They do incorporate this variable in a final analysis, but they also incorporate that pretest variable and mean pretest, but then they go through centering those variables and so forth. And as I said earlier, I don't want to kind of gum up the work, so to speak, by going into all that. So I'm just going to run one more model just where we have gender or gender identification added as a predictor of the variation in our outcomes. So what I'll do is I'm going to click on Analyze, go down to Mixed Models right here, and we'll click on Linear again, and we'll just kind of click through. And so we'll add in gender as a covariate. So keep in mind that gender in our data set is actually, it looks like it's also basically effect coded, where a coding of 0.5 indicates a person identified as female, and then a negative 0.5 is identified as male. So we'll click on Fixed up here, and at this point we'll highlight the gender variable and index variable. Leaving this as factorial, we'll click on Add, and I want to remove this gender variable by right there. So basically, as we're adding in additional predictors, if we later on, I know in the chapter they add in school level predictor, you'd be adding them in the same way, basically as interaction terms, like we're doing right here. So whether you're talking about at the student level or you're talking about at the school level, any covariates that are being added in, you would want to model it using these interactions, as you can see. So now we'll click on Continue, and then we'll click on OK once again. And so now you can see that we have 12 parameters that are being estimated right here. And the reason why is because we're testing gender effects or the effect of gender identification on each of our outcome measures. So that's why we've added 2 more parameters to our model. And so as we scroll down, you can see that with respect to the estimates of fixed effects, you can see the regression slopes right here. Really, all of the other results are pretty much the same. With respect to our gender variable right here, you can see, given the coding of that variable, that individuals identifying as females scored higher than those identifying as male, and that difference is significant with respect to, and that's with respect to the intention variable. With respect to the knowledge variable, we also see a gender difference with persons identifying as female scoring higher than those identifying as male, and that difference is statistically significant. So that is going to pretty much wrap up this video presentation. As I said before, when it comes to this type of modeling, it's extremely complex. There's a lot of moving parts, and so I do encourage you to be sure to continue to read up on this particular topic, and in particular, if you want to kind of flesh out these this discussion with respect to these this example, certainly visit that Pittock and Stevens 2016 text. Again, this is in chapter 14 of that particular text. So that concludes this video presentation, and thank you for watching.